So for any good performance, if you want from Gromax, you have to have the recent version of the compiler installed in your system. It can be either GCC 4.7 or Intel 12.0 or any newer compiler. If you are doing it in Ubuntu, I'll show you what is the command that you have to use. In Ubuntu, all this compiler and all these are already there. You just have to update it or install it. The other thing that you need is CMake software. Suppose from, if you are installing Gromax 4.6 version onwards, then you have to use the build system CMake. And CMake version also should be higher than 2.8.0 or higher version you require. Again, you can download the CMake software from www.cmake.org. So you will get a tar file from there, tar folder you will get. Similarly for the FFTW also, because the simulations that you do using Gromax, it makes use of fast Fourier transformation. So you have to have a software library to perform these fast Fourier transformation. And that is why FFTW is also required. And that has to be version 3 or higher. So these are the three things you will require apart from the Gromax tar file. CMake, FFTW, you will get it as a tar file. Gromax also, you will get it as a tar file. So these three things have to be there. Are you installing it in Windows or are you installing it in Linux system or Ubuntu?
I think most of them will install on Windows.
Okay, so do they have the in Windows also you can have a separate corner for Ubuntu. So if you can download the Ubuntu in Windows also, it makes your job easier. It's a little bit faster. Okay. If you are doing it in Ubuntu or if you are doing it in Windows also using SSH terminal and all, then you have to first log in and you have to go to your respective terminal. In order to install your compiler like G++ or C++, you don't have to download anything. You just have to type out this command. Sudo, then you have a space, apt, then space minus get. This minus get is together. Install G++, space, there is no space, dash 4.7. This 4.7 is the version of G++ compiler. If you do this, it will ask you for a password. That password is the same as your PC password. So you have to just enter that password and then it will automatically get installed. So once you have typed out this command, you have to type out sudo apt minus get install build minus essential. So this is going to install the software properly in your system. And if you already have this compiler, this will just update your compiler from the older version to the newer version.
Okay.
Please let me know if I can proceed.
Yes, ma'am.
Okay. Then how do you install CMake in Ubuntu? The reason I'm showing it in Ubuntu is because Ubuntu is free. And running simulation in Ubuntu is very fast compared to running simulation in any Windows. So even in Windows, you can install Ubuntu or you can do a partition as many people do. Some part of it is allotted to Ubuntu, some part of your C drive will be allotted to Windows. So that also you can do, or in Windows only without making partition, you can install Ubuntu. So again, same thing, you have to go to the terminal. If you have the CMake file downloaded from their website, the tar file. So first that tar file, you have to unpack it. So the command for unpacking a tar file is tar space minus xvzf, then the CMake version that you have downloaded. It has to be 3 version. 3.0 onwards, it has to be. So what I have downloaded is 3.9.0 tar.gz. Once you type out this command, your tar file will be extracted. Then you have to make a folder for CMake. So what you do, you go to that folder that it has extracted all the files of cd space CMake 3.9.0. Inside that folder, you have to type out /configure. So it will start configuring the CMake folder. Once it is configured, you have to make sure it is installed properly. So what you do then, you have to type out make -j6, next command, and then after that sudo make install. When you type out sudo make install, it will again ask for password. If your PC is protected by any password, or if it is not, password is not there, it will not ask for any password. It will directly install the CMake. Once CMake installation is done, at the bottom, you can see it will be written CMake installed successfully. After you install CMake, first thing you have to install is compiler. Then you have to install CMake. Only after you install CMake, you can install FFTW. That is your fast Fourier transformation. Again, FFTW also, it has to be higher order of higher version like 3.0 onwards. So what I have downloaded is 3.3.6 from the official website of FFTW. And all these are free. You don't have to pay anything anywhere for downloading and installing these packages. Again, since it is a tar.gz file you will get, you have to unpack it using the same tar command, that is tar -xvzf, then your tar file name. It will extract all the files and it will create a folder named FFTW, the version of the file. So you go inside that folder. For going inside a folder, the command that is used is cd, change directory. Once you are inside the folder, you have to configure the fast Fourier transformation. So in order to configure it, same command /configure. Once it is configured properly, it will ask, you have to install it. So same thing, make -j6 and sudo make install. The installation and procedure for FFTW and for CMake is same. Only the file name you have to enter it different. That's all. Once all these three are installed successfully, then you will move on to installation of GROMACS. Any version of GROMACS you can download. Preferably, you can download the latest version. What I have downloaded in my system is 5.1.4. So this also comes in tar.gz format. Again, you have to unpack it. And all these things, what you are doing, what you are unpacking, or wherever you are installing, it has to be in the same working directory. You cannot install GROMACS someplace else, and you cannot install FFTW or CMake someplace else. It has to be in the same working directory. So you unpack the tar file of GROMACS using this command, tar -xvzf GROMACS, whichever version you are downloading. Then it will unpack and it will create a directory of GROMACS of the version that you have downloaded. You go inside that folder, cd space GROMACS, whatever version you have downloaded. Then you have to create a folder named build. So you will type out mkdir, make directory build. Then you go inside that build directory and you have to type out this command. What is this command? CMake, this path that is given over here, home/Sonanki/downloads/GROMACS. It is the path of my system where I have downloaded GROMACS. Similarly, you have to see the path where you have downloaded. Suppose you have also downloaded, in your system's name is XYZ, and you have downloaded GROMACS where in downloads folder or in your D drive or C drive or E drive, wherever you have downloaded, this path has to change accordingly. So this is where my GROMACS folder is downloaded. That's why I have taken this path, and it has to be under single quote. Then this command, space -dgmx_build_own_FFTW is equal to on. So it will take into account it is going to the FFTW folder that you have installed. From there, it will take all the necessary files and install it. Once this is done, again, make and sudo. So make and sudo will install your GROMACS properly. Now, in order to get all the commands, to work properly in your window, this is the command that is used. Source user local gromax bin gmx.rc. It will go when you are installing or unpacking the gromax folder. In that folder, you will have source folder. Inside that, you will have user USR. Then you will have local gromax bin folder. In the bin folder, you will see, you will get everything, each and every command is given over there. Whatever command you require in Gromax, whatever command is there in that version will all be available in this bin folder. If you click on any one of the command, if you just open the command by giving the file name as vi space whatever the command is, it will give you details about the command. The code of the command will also be given there. So if you are interested in knowing how a particular command is working, how it is calculating certain properties, the code is already there installed in your Gromax folder. You just have to play around it. And it's always better to know what the code is rather than blindly just using the command. And after this is done, executed, you just type out any command of Gromax. Here I have typed out pdb to gmx. You can type out grow mpp. You can type out g_rdf. Any command you just type out to check whether your Gromax is installed correctly or not. If any of the commands are not working, that means it has not been installed properly. And one more thing you have to remember, when you move on to different version to version, the way you type out your command also changes. In some case, in the older version, g_rdf will work. In the newer version, g_rdf will not work. So g_rdf_mpi is what is going to work. So different version, the first part of the command remains the same, but after that, either it is _mpi or something else is there, or gmx_rdf is there. Like that, the command changes. So you have to check accordingly which version you are downloading, and in that version, in what format your commands are given. So that only you have to type out any one of the command you just type out to see whether you have installed it correctly or not. Once it is correctly installed, it normally does not give you any error while installing. Once it is installed, it is ready to use. Now there is one more thing that you need to run Gromax. Not to run Gromax, to build your system. Suppose you want to study a bilayer system, or you want to study a system which has nanoparticles in it, where you are studying any nanoparticle, or very simple, you are studying only water. So for that, you need to build your system. In order to build your system, the software that is used is Pacmol. Again, Pacmol is a completely free software. You can download the package from its official website. When you go to the official website of Pacmol, you can see, this is the link. You can see there, they have given lot of example of how for different type of system, how your input file should look like. It has given very simple system for water, for mixture of solvent, for bilayer it is given. If you have a spherical system, how your PDB, what is the form of your input file should look like. Everything is given over there. You just have to, go through the web page very clearly. So once you go here, you just have to download it. It will ask you for your email ID. Any email ID is fine, whether it's official or your personal mail ID. You can download it. Once you download it, again, it will be downloaded as a tar file. So what you have to do, you have to unpack it using the same command tar -xvzf pacmol.tar.gz. Once it is unpacked, it will create a directory called Pacmol. You go inside Pacmol and then you type out make. Once you type out make, it will say at the end, Pacmol built successfully. So this is 3-step installation for Pacmol. Once you have your Pacmol, once you have your Gromax properly installed, you are good to go. So first I'll start, and then if you want to plot your graph using a free software, apart from your even Microsoft Excel and all, they are all, it's not free. XM Grace in Ubuntu is free. It's a tool which makes a two-dimensional plot of any scientific data. What does GRAY stands for? Graphing Advanced Computation and Exploration of Data. And it runs in any Ubuntu system. Same thing for XM Grace to be downloaded in your system, you don't even need any tar file and all. You just have to type out this command in your terminal. Sudo apt space minus get install Grace. So it will install Grace. If you have Grace already installed in your system, it will update it, or else it will install it. So XM Grace is a free software which will give you a two-dimensional plot. Now this is the overall pipeline as to how an MD simulation is done. So you take, first of all, you have to prepare the topology. What is topology? Where you write all the force field parameters, where you write all the information about what is the bond length, what is the bond angle, what is the bond force constant. Every detail about your system is given in the topology file. Once you have the topology file, you have to create your box, your system. Then suppose your system, you have only solute, you have only protein, let's say, for example. You need to add solvent molecule also. So next command that you will use is solvate. Solvate is used to add solvent molecules. By default in GROMACS, the solvent molecule used is water. You can use any other solvent of your own choice if you have the solvent's proper structure. Once you have your system ready, you will need GROW-MPP. What is GROW-MPP? It is a compilation of all the parameters required to run a simulation. Whether you are doing your simulation in NPT or NVT, which integrator you are using, which thermostat are you using for keeping your temperature constant, which barostat you are using to keep your pressure constant, all the details will be provided, will be given in this GROW-MPP file. Once you are done, this is what your system is now prepared. Once your system is prepared, you will go for minimization using GROW-MPP command and MD-run command. MD-run means it is going to run your minimization. Once your energy minimization is done, then you will go for equilibration. Again, GROW-MPP file is where all these details are given. GROW-MPP file you modify based on NVT equilibration first. Then you do a MD-run. MD-run will run the equilibration. Once it is done, you perform NPT equilibration. Once it is done, you run the NPT. Then once equilibration is done, you have to do a production run, that is full MD simulation. That is again GROW-MPP file changes are required. So that will, once the full MD is done, you will get trajectory file. Once you get the trajectory file, you can convert it, you can use it to get any result you want of your own choice, any dynamic properties, any structural properties you want to calculate, everything you will get it from the trajectory file. So what you need to configure a calculation before running it. That means you need to have a proper structure setup first, and you need to gather all the parameters that is required for your simulation, which is contained in the form of an MDP file, molecular dynamics parameter file. That is what it stands for. The structure of your system is required, and topology file. Topology file, as I've told you, what is the bond length, bond angle, all those things are specified in that. In case of MDP file, there is a certain format. You can get it from your GROMACS website, but you don't need all the parameters for your or for all type of simulation. There are certain parameters you don't require for your simulation. You don't have to add that. So depending on system to system, your MDP file format will change. So what you have, if you have your MDP file, you have your structure, you have your topology file. These three you require to run GROW-MPP command. Once you run the GROW-MPP command, you get a file in form of TPR. It is a binary file. It is a non-editable file. This TPR file only you have to run. for your long MD or for equilibration. Once your MD run is done, you get the result in form of a trajectory. From trajectory, you can calculate energy, you can calculate diffusion coefficient, you can calculate power spectra also. So many things you can calculate only with the trajectory file. So this is the overall diagram as to how MD simulation works. Now I'll give you an example starting from a very small system. I'll first start with liquid argon, for which the very first simulation was performed by Rahman and Stillinger, molecular dynamics simulation of liquid argon. So there I will show you and give you details of each and every file, what everything stands for. So first I'll start with what are the input files that is required for MD simulations using GROMACS for liquid argon. First thing that you need is the structure file. Structure file means what is the file, what is the structure of argon? Argon is one atom only. It can either be in form of .gro or .pdb. What is .gro? .gro stands for bromo structure file, and .pdb stands for protein data bank file. And the difference between PDB and GRO file is, in PDB file, if you see, you will only have X, Y, Z coordinates of that particular molecule. Whereas in GRO file, if you see, which I will show you later on, you will also have velocities for each and every atom apart from the coordinates. So first thing you need is a structure file of the molecule or of the system that you are trying to do a simulation of. The second file that you require is a molecular topology file, that is .top file. This is the extension of the file, .top. What it contains complete detailed description of all the type of interaction present in your system. It's basically a force field parameter file where you have bond angle, bond length, bond force constant, dihedral angle, how many bonds are there, what is the sigma value, what is the epsilon value, what type of potential you are using to do the simulation. All the details will be contained in the topology file. The third file that you require is a .mdp file, which is the molecular dynamics parameter file. As I had told you earlier also, this is the file that will contain you as to for what, how much time you are trying to run the simulation for. What is the thermostat you are using, which is the barostat you are using, what is the temperature at which you are trying to do the simulation, what is the pressure at which you are trying to do. So all those details will be contained in the molecular dynamics parameter file. And then you need an ITP file. ITP full form is include topology. These files are included in the topology file format only. So now I'll start with the structure file. How do you generate initial configuration for any simulation? Suppose for argon, you want to generate initial structure. You can generate it from the software PackMol. You have already installed it. What you need for it? Now for PackMol, you will get initial configuration in the format of PDB, that is protein data bank format. So first you have to log into your remote server if you have, or you can log into your system where you have installed Ubuntu, in Ubuntu where you have installed GROMACS and PackMol. Either you can do it in your own system or you can log in to your remote server. You can go to your home directory by using the command cd, and then you go to the PackMol directory. Here I have shown using a remote server. So this was the server name. And then I am typing out the command cd space PackMol. So it will take me, it has taken me to the directory PackMol. You can see it has changed from GROMACS to PackMol. Once I go to PackMol, sorry, yeah. Just 1 second. This file over here, what is shown in the black diagram, this is Ubuntu installed in my system, in my laptop. In Windows, it is installed. So that is why it is showing here as Sonanki @Sonanki. So this is the path where GROMACS is installed. This I have told last time also when GROMACS installation was going on, that this is the command you have to use: source user local GROMACS bin. to ensure that Gromax is installed successfully. Now here I am going, I already have a folder named packmol. You can see over here. So I have just written cd space packmol. So it will take me to my packmol directory. So once you are inside the packmol directory, what you can do, you can type ls. It will list all the files that is present in packmol directory. So this is all the files that are present in packmol directory. So what you will require now, you require the structure file for argon. So you can open or you can make a file argon.pdb using vi command. Vi will create a file. So this is how the structure of PDB file format looks like. You have here header, then in the next line, HETATM, then space 1, argon, space argon, then 1, then 000 is written. So what does all these things mean? This last three columns are the XYZ coordinate of argon atom. How do you create a PDB file? You can create a PDB file using either Gauss View or Argus Lab or Discovery Studio. Using any of this, even ChemDraw, any of this drawing software, you can create a PDB file. If it is a very known system like water, methanol, ethanol, any solvent, you will get it easily. Or you can get the PDB files from a website which is known as Automated Topology Builder, ATB website. From there also you can download PDB files for certain molecules. Even the Gromax parameters are also available. That is, the topology file is also available there. So that also you can download. And it's also a free website, ATB website. So there are these many websites where you can make the PDB file, you can download it. Or suppose you have a new molecule for which you are not getting the proper PDB file or the topology file, you can draw the structure in any of the softwares, either ChemDraw or Argus Lab or Discovery Studio or Gauss View or ChemSketch and all. You draw the structure, you save it as PDB, you upload the structure in Automated Topology Builder. It will run the file for you and it will give you the topology file also. So there are many ways by which you can get all this information. So once you are done with your PDB file, what does each and everything mean? Now, column number 1 to 6, it is a record name, that is the atom name. Then column number 7 to 11 is an integer number, as you can see, which is the serial number of the atom. Here you are taking only one argon atom because in argon atom, there is only one atom over there. So serial number will only be 1. The moment you move on from argon atom to say methanol or ethanol, there are more than one atom. So then you will have another line also with 2, 3, 4, 5, 6 and all. 13 to 16th column is the name of the atom. What is it over here? It is argon. The 17th column is the character. 18th to 20th is again the residue name. I have given the atom name and the residue name as same. You can change it also. It depends on you. The 22nd column is again the character name. That is a chain identifier. It has to be same as your atom serial number. 23 to 26 is an integer residue sequence number. Then 31 to 38, 39 to 46, and 47 to 54. These last three, they are coordinates along x-axis, y-axis, z-axis. And these coordinates, please remember, it is given only in angstrom. What you get in GRO file is in nanometer. What you get in PDB file is in angstrom. So these are all coordinates in terms of angstrom. So this is the detailed description of a PDB file, what each and everything stands for. Now, how do you generate? You open the file in packmol website. When you go, you will get input file format also. Or if you want, I can send you these files also. If you open the argon.inp file using the command vi, you will see this type of file coming up. This, I have used it as an example from the packmol website only. First line is written as tolerance. Then you have file type. Then you have output, structure, number, inside cube, and end structure. Now, what does this mean? Tolerance is given as 3.0. That means the distance between two atoms should be at least 3 angstrom. You cannot, if you write it as 0.1 or if you write it as 1 angstrom, your PACMOL will show error and it will not compile only, because you have kept the distance between two atoms, very small distance you have kept. So your distance has to be this tolerance, you will put it based on the size of your system, size of your atoms that you are considering. So here I have taken it 3 angstrom. Then file type PDB means your input file type is PDB form. Your output file will also be in form of a PDB. Output is written as liquid argon.pdb. Liquid argon.pdb is the name of your output file. You can change it to whatever you want, but the format will be .pdb. The next line is written as structure argon.pdb. This is where you give the input file structure name. If your structure name is argon.pdb, you will write it as argon.pdb. If it is ar.pdb, you will write it as that. Any mistake over there, your file will not run only. Then next line is number 567. Inside cube, that means you have taken 567 argon atoms in a cubical box with box length of 30 angstrom. The keyword inside cube here is used. Then it is end structure. So it is ending this program. You can take a 40 angstrom box, 50 angstrom box, 10 angstrom box, but your number of argon molecules will change accordingly. You need to know how to calculate number of molecules that you want to take for a particular simulation based on the density of the system. For liquid argon, it has a particular density. You can know the density. If you know the density, if you know the box length, from box length, you can calculate the volume. Then you can easily calculate how many number of solvent molecules you require or how many number of molecules you require in that particular box length. The same number will not be true for 40 angstrom box length. So it will change based on number to number box. It will vary based on box length to box length. So this is the file format for initial configuration in PACMOL. Once your file is ready, once your this argon.inp is ready, you have to execute it. How to execute in PACMOL file? Just type out this command, /PACMOL space less than argon.inp. This is the input file name for argon simulation, and then you type enter. So this is the command you type. Once you type enter, something like this will be displayed on the screen. Solution written to file liquid argon.pdb. You will get it as success and running time, how much time it took to execute your file. If normally PACMOL executes in a very few seconds, in fraction of second, it will execute your file unless something is severely wrong with it. If something is wrong with it, it will keep on going, keep on going. But that cannot, but that when it keeps on happening for a very long time, then you have to know that your file, something is wrong there, missing there, or some input format you have given it wrong. That is why it is not working out. So you need to modify it accordingly. So once your PACMOL liquid argon.pdb file is ready, you have your input file ready. If you open the liquid argon.pdb file, this is how it looks. So first you will have title that is built with PACMOL, then remark PACMOL generated PDB file. Again, you will have remark, then HET hetero atom, then labeled as 1, 1, then 2, 3, 4, 5, different number of atoms. Then these are the coordinates of each and every argon atom inside your box. Not one single coordinate should exceed 30 over here, because your box length itself is 30 angstrom. So not one single XYZ axis should be more than 30. It has to be within 30. So these are the coordinates of each and every argon atom in angstrom, because this is a PDB file. Now, PDB file is not the format that you work in GROMACS. In GROMACS, if you have to work, you have to convert your PDB file into GROMO structured file, that is .gro file. So in your directory arg, you create a directory name argon using the command mkdir argon. So it will create a directory. Then you copy that liquid argon.pdb from the pacmol directory to argon directory using this command. That copy, cp means copy, liquid argon.pdb dot. That means it will come out of this directory. Then it will copy this to argon directory. Type out enter like this. Once it is done, then if you type out this particular command, you will get initial configuration in .gro extension. Genbox -h is what you type. What is -h used for? -h will tell you what this command does. It is used for, it stands for help. So it will give you all the details. What are the input files you need for running Genbox? What is the form of output file you will get? And everything in detail it will give you. It will give you the entire thing, that what it does, how it does, everything you will get it if you type out -h command. So Genbox, that means it will generate a box, -cp liquid argon.pdb. That is, it is taking that liquid argon.pdb file, -o conf.gro. -o is the extension for output. So -o stands for output. So output will be written in conf.gro. What is conf? It is configuration. You can write it argon.gro also. These file names actually depend on whatever you want to give. -box space 3.0, 3.0, 3.0. That means it will create a box of 3 nanometer box length, cubical box, because the box length we have written in pacmol was 30 angstrom. Here you have to do everything in nanometer. So box length is taken as 3.0, 3.0, 3.0. Then if you type out enter, you will get your file format in .gro format. Once you have that GRO file, you can use the vi command to open the file and see what it is written. It will give you the coordinates in nanometer, and it will also have velocities of argon atom. That's the difference between GRO and PDB file. Now, what is there in topology file? As I have told you, topology file, it contains force field parameters, that is Lennard-Jones parameters. The potential normally used for simulations are Lennard-Jones potential, Lennard-Jones types of potential. There are many other potentials also, like Morse potential is there. Then in Lennard-Jones also, normally 1261 is the most commonly used. Apart from that, you have many other potential models, which Professor Murrell has already discussed. What are the different Lennard-Jones parameters that we require? It is sigma, epsilon, charge. I hope all of you know the form of 1261 potential. So if you open the file topol.top, this is how it looks. This, whatever is given in semicolon, that's a comment. So that will not be taken into account. Whatever is not in semicolon is the term that will be taken into account. So what is written here? NB function. NB function means non-bonded function. Bottom of NB function is written 1. So when NB function you are writing 1, that means you are using 1261 potential. When you are writing it as 2, that means you are using exponential 61 potential. Then combination rule. Com rule means combination rule. If you know the form for Lennard-Jones potential, you will know that sigma and epsilon are geometric and arithmetic mean. So combination rule 3 means epsilon AB is taken as epsilon alpha alpha into epsilon beta beta to the power half, and sigma AB is calculated as sigma AA alpha alpha into sigma beta beta to the power half. Whereas combination rule 2 is different. One is taken as geometric mean, the other one is taken as arithmetic mean. Then gen pairs, generate pair of interaction. Yes, you want to generate pair of interaction. Fudge LJ, fudge QQ. They are not used for argon atom because they are mostly used for triatomic and polyatomic molecules. Then you have atom types, detailed of what your atom is. Name, argon. Mass, what is the mass of argon atom? 39.948. Then charge, argon is neutral, so charge is 0.0. P type, what is the type of atom? It is atom, so A. Sigma in nanometer, epsilon in kilojoule per mole. Sigma epsilon, again, it is Lennard-Jones parameter. These details, if you are not getting it anywhere, when you install GROMACS, automatically certain force field parameters also get installed, like OPLS directory, Amber, Charm. They all also get installed in top folder, TOP folder. In that, if you go to OPLS, if you go to FF non-bonded.itp, because these are all non-bonding parameters. If you go there, you can find out these values. Sigma epsilon will be given for many types of atom, many molecules. This will be given already. Then what is written? Include argon.itp. Next slide, I'll show you what is there in argon.itp. What is your system name? System name is liquid argon. Then molecules. What is your molecule? Here it is written as AR. You have to remember whatever is in your GRO file, the name of your molecule or atom. If it is written as capital A, small r, here also you have to write capital A, small r. If you write both capital A, capital R, it will not take. So file name or molecule name, residue name, whenever you are assigning, you have to be very careful about. Then you have number. What is the total number of atoms you have taken? That is 567. Any mistake, small mistake here and there, the simulation is not going to run at all. So once you have changed everything in your top file, what is there in the ITP file? ITP file, this is what is there. So what do you have? Molecule type. Molecule type, you have to define detailed description of the molecule. So name is argon, NREXCl. You have to define how many bonds, non-bonded interactions are excluded in this molecule. Then what is next? You have atoms. In this directive, what and all you should define? NR. NR is the serial number of atom in molecule. You have only one atom, so serial number is 1. Type is, you have to define the type of atoms in the molecule. Then residue, residue number. Which residue number is this? You have argon atom, only one atom, so residue number is 1. Then residue. What is the residue name? Whatever name you have put in .gro file, the same name should come over here. Atom name, that also should be the same. Then CGNR, that is, you should write atom name of each atom or molecule. Sorry, you should write charge group number. This belongs to the first residue number, so 1. Charge, what is the charge on argon? It is 0. So you will write it as 0. And then mass, you have to write mass of each and every atom of your system that you have taken. So this is what is there in ITP file. Once you are all these files are prepared, you have your GRO file, you have your ITP file, you have your top file. What you all need is MDP file. That is, first step is energy minimization. You have to make your structure. The moment you start your simulation, it is not properly minimized structure you start off with. So first you do a global minimization. So how it is done? It is done using this em.mdp, that is energy minimization dot molecular dynamics parameter file. This is the file format for it. What are the parameters? Integrator. Integrator means which algorithm are you using to calculate the minimum energy structure of your system. Here it is steep algorithm, that is steepest descent minimization is used. This is the simplest algorithm that is used and it works quite well for different systems. EM total is 1000.0. That means stop minimization when the maximum force is less than 1000 kilojoule per mole per nanometer. EM step 0.01. This is the step size. So if you are giving n steps, that is total number of steps is 5000. So it will start from 0.01, then 0.02, then 0.03 up till 5000 unless you get a force which is less than 1000 kilojoule per mole per nanometer. It will carry on this process. Then what are the other parameters? NST list is equal to 1. Frequency to update the neighbor list and long range forces as to how many times you are taking into consideration as to around each argon atom, how many times different argon atoms can come. NS type grid. How do you determine the neighbor list that around this argon atom or around number 50 argon atom, how many other argon atoms will come? That is determined using grid method. R list is 1. That is the cutoff. You cannot, in a 30 angstrom box length, you cannot give the cutoff as 30 angstrom. So you have to make a cutoff length for determining your neighbor list, for determining your bonded interaction, non-bonding interaction. And that distance should be less than half of the box length, either equal to the box length or less than half of the box length. It cannot be more than half of the box length. Coulomb type. In order to treat long range electrostatic interaction, particle mesh evolved sum is used. R Coulomb RVW is for short range electrostatic cutoff and short range van der Waals cutoff. You can see the cutoff length is 1 nanometer, 1.4 nanometer. In all the MDP files, whatever file is in GROMACS, all the format is in, all the units are in terms of, distance is in terms of nanometer, energy that you get is in terms of kilojoule per mole. Please remember this. And as you can see, your box length is 3 nanometer. So all these cutoff lengths are less than 3. Then PBC. PBC is equal to XYZ. PBC is periodic boundary condition. Suppose you have a box here in the center. In order to, during your simulation, it may happen that one molecule from your box, it may step out. So your number of molecules may decrease. In order to make the number of molecules constant in your simulation, periodic boundary condition is used. What does that mean? You assume that your box is surrounded in all the 3 directions with equivalent boxes, mirror images of the same box. So the moment one box from center is going out from here to here, from the other box, one more molecule is entering the other box. So your number of molecules are maintained constant using PBC condition. So along all the 3 axes, PBC is used. This is the detailed description of energy minimization file. That is your MDP file. Once you have all these files, you have to generate a TPR file. How do you generate a TPR file? Using the command growmpp. Growmpp, and what are the input files required? If you type out growmpp -h, it will show you what are the input file required, what is the form of your output file. So -f, for any MDP file, the flag used, this F, C, P, O, these are all known as flag. So this flag that is used is -f. Then you need your structure file. So -c conf.gro. -c is the flag for GRO file. -p is the flag for topology file. Then -o. -o always stands for output. So -o em.tpr. First you will generate a TPR file. Then -max_2. That is, it will ignore 2 warnings maximum. You can give it also, you cannot give it also, it doesn't matter. Then if you type out enter, you will get a file name in TPR, em.tpr. So what you are doing here, you are combining the structure file, topology file, molecular dynamics parameter file, and sometimes you may require index file that will come later on. In order to generate an input file in TPR extension. What does this TPR contain? It contains all the information required to start a simulation using GROMACS. The TPR file extension, it stands for Portable Binary Run Input File. And it contains the starting structure of your simulation, the topology file. This will combine all these 3 files together. And since it is a binary format, you cannot read it with a normal editor. How do you read a TPR file? You have to type out gmx dump minus SEM.TPR. Using this command, it will display it on the screen itself, that what and all information is contained. It is basically a combination of all these three files together. Once you have generated the TPR file, so this is how you will get. This will generate roughly 1 MB of data like this and all you will get. Once you have done this, you have to type out MD run. So MD run will run the energy minimization now using the TPR file. So before you actually type out the command, again you can do is -H, that is help command you can use. So what will it give you? MD run -H, it will display what are the input files you need, what are the output files you require. So MD run -V -SEM.TPR, -S is the flag for TPR file, -OEM.TRR. TRR is the format of a trajectory file only, -CEM.GRO. Why it is labeled as EM? Because if you label it as the same file, conf.gro or conf. something, it will give you this, it will override the conf.file. So you want this for energy minimization. So EM will specify energy minimized files, -EEM.EDR. EM.EDR will contain all the energy related file, -GEM.log, then -XEM.XTC. This is the trajectory file. Once you type out enter, now instead of typing this entire thing, you can do a shortcut also. MD run -V -BEFFNMEM. If you type out this command, all these files will be generated with an initial of EM. So you don't actually have to type out all these things. You can use a shorter command also. Now, once your energy minimization is done, this is how it will look. Steep is decent. Tolerance is what you have given, 1000 kilojoule per mole per nanometer. So 1.00 E plus 03. Number of steps you have given 5000. See, step number 1. What is the potential energy? What is the maximum amount of force? On which atom the maximum amount of force is exerted? So here you can see your steepest descent has converged to F max in less than 17 step. So it has not gone beyond 16 step. What is the potential energy at that step? This is what your value is. Maximum amount of force, normal of force. So your steepest descent energy, writing lowest energy coordinate. So the EM.GRO that you will get is the lowest energy coordinate. Once you have your lowest energy coordinate, you are going to use it to run your equilibration and full molecular dynamics. What and all you have in full MDC file? The first thing you have to specify is integrator. What type of integrator are you going to use to integrate Newton's equation of motion? I'm using here MD. MD is the basic one, which is leapfrog algorithm is used to integrate equation of motion. You have many other algorithms apart from leapfrog algorithm. You have velocity Verlet algorithm. Many others are there. Here I'm using leapfrog. So for leapfrog, the command that you write is MD. The next line will be your DT. What is DT? It is the time step that is required for MD simulation. You can use in GROMACS a time step up to 10 femtoseconds. After DT, you will have N steps. That is the total number of steps you want to do you want to perform your simulation for. And if you multiply DT with N step, that will give you total simulation time. Then you will have NSTX out. These numbers, you can change it according to you. That means X out means it will write coordinates of each particle after every 100 into DT time. DT is the time step that you give. Normally 2 femtosecond is the standard time step that we use, that I use for my purpose. Then you have NST V out. V out means velocities of each particles will be written after every 100 into DT time step. Then NST F out. Force on each particle will be written. Then NST log. Energy of the system will be written in log file after every 90,000 into DT time step. Then NST out. It will write trajectory of the whole system after every 500.dt time. Trajectory file is the one that you require. So even if all these numbers, NXT, X out, V out, F out, log, even if all of these are zero, please remember not to put zero over here. NST, XTC out. Because trajectory file is what you will need for analysis or to get all your results. Then is NST list, which is equal to 10. That is your neighbor list. Your neighbor list means around each and every atom, how many which atoms are coming, that will be updated after every 10 into dt time step. What type of software or what type of algorithm are you using to check that? That is grids. Then Coulomb type is PME, that is particle mesh evolved, is used to calculate long range interaction. You can also use reaction field method or evolved sum method. Then R Coulomb is 1. This is a cutoff distance for Coulombic interaction. Again, the cutoff will depend on your system size or box length that you take. PME order is 4. That means electrostatic force have an accuracy of this range. Then you have van der Waals type. Again, you will have to have what is the cutoff distance you are keeping for van der Waals interaction. Then T couple, that is temperature couple. Which algorithm are you using? Here I have used velocity rescale. So V rescale is written. Temperature coupling group, which is the group that you want the temperature to be fixed. If your system has only one type of molecule, that means your entire system is in that group. Or if you want to specify certain atoms only in that those atoms only should temperature be fixed, then you have to mention it here. Then reference temperature, I have taken it as 298. Constraint, no, that means molecules of the systems are flexible and you are using force constant to make the bond flexible. Constraint is equal to all bond, that means your system is all molecules of the system are rigid. What is the algorithm you are using to fix the bond length and bond angle during simulation? It is links. Linear constraint solver. There is shake, there is settle. There are different type of algorithms. Normally for liquid argon, it is not so much required, but the moment you move on to water or any other system, you start having bond angle, bond length. So that bond angle, bond length of water molecule or any other molecule has to remain the same throughout the simulation. That cannot change. To make sure we add these algorithms. Then it is pressure coupling, Berenson. I have used Berenson barostat to keep the pressure constant. What is pressure couple type? Isotropic. That is, in all the directions, the pressure has to be kept constant. Then tau P. Then is compressibility. Compressibility depends on system to system. So you have to check the compressibility for different system, what is it you are getting, and then you have to change the value. Reference pressure is given as 1 atmosphere, 1 bar pressure. Generate velocity, yes, that means it will give initial velocities to each and every atom in the system. So this is your entire MDP file. Now, how do you perform MD simulation? You already have that energy minimized configuration from your energy minimization. This will be the input file for your production run. And your MDP file will be full.mdp. Topology file remains the same. ITP file remains the same. So using this GRO, this MDP and your topology file, you will generate full.tpr using this command. Same thing, only your MDP file name will change. Here your input structure will be em.gro instead of conf.gro. Your output file will be full.tpr instead of em.tpr. Now you have to do MD simulation using this command, MD run. Either you can type out the whole command, or if you just type out MD run -v -DEFFNM space full, it will give you the same set of result. So once you are done, you will get different type of output files. You will get full.gro, full.xtc, full.log, full.trr, full.edr. Full.gro will be your output file, structure file. Full.edr will contain all the energy related file. full.xtc and TRR will contain the trajectory files. Once you have the XTC file, there are different properties you can calculate. So one structural property I'll show you, which is known as radial distribution function. Radial distribution function is something that you can correlate it with experimental data as well. From neutron diffraction, you get radial distribution. So those two, so radial distribution is something that can be correlated with experimental results as well. So how do you calculate? Suppose you want to calculate radial distribution function between two argon atoms because it is a liquid argon simulation. So first you have to create an index file which will contain index of all argon atoms. How to create an index file? Using the command make_ndx. Again, if you type -h, it will show you what is the input file, what is the output file. Here, the only input file that you need is your GRO file. Any GRO file will work. Either your initial one or your energy minimized or your full.gro. So -f conf.gro -o index.ndx. You type enter, then you type Q to save and exit. In order to find out RDF or radial distribution function, you type out G_RDF. If you type out -h, it will show you again what is the input file you need, what is the output file format you get. In input file, of course, you will need an index.ndx because that's why you have created it. The flag for index.ndx is -n. You will require XTC file. For now, all the analysis of getting for all results, XTC file is required. You will require TPR file, full.tpr, and your output will be rdf.xvg or whatever you want to name it, but the form will be .xvg format. Then you type out enter. It will ask you to select two groups, that between which two groups you want to calculate radial distribution function. So here you have 0, you have 1, you have 2. All the groups are same because you have only argon atoms. So you can type out 2 and 2 or 1 and 2 or 0 and 2, whichever combination you want. It will give you the same result in case of argon atom. If you type out both 2 and 2 or 0 and 1 or 0 and 2 together, then you just have to type out xmgrace space file name. If you type out xmgrace space your file name, that is rdf.xvg, this is the plot that you will get for liquid argon. What is it? This side is y-axis is G of R, that is radial distribution function between two argon atoms. Your x-axis is distance between two argon atoms. And you see after a certain distance, beyond 1, radial distribution function becomes equal to 1 only after a certain distance. The number of peaks in RDF will correspond to number of solvation shell your molecule has. So here you are getting 1, 2, and very slightly third peak. For these type of system, it is not very useful, but when you do simulation for, say, I have given you example for ion pairs and all. When you take ion pair in, say, water or something. For sodium, we know how many solvation shell exist, how many hydration shell exist, and what is the coordination number of sodium in the, if you take water as solvent, normally we say sodium, for sodium atom coordination number is 6. You actually get a RDF diagram like this around sodium for water. If you integrate it till the first minimum, that should give you around 6. And that actually comes around 5.8 or 5.9. So that means what you are getting from simulation, what you are getting from experiment is the same thing. So you can actually cross-check whether your simulation is giving you correct result or is giving you result closer to experimental data or not. Now, similar thing, you can calculate also dynamic properties like diffusion coefficient. So with the help of the command G_MSD, mean square displacement, it uses the method of mean square displacement to calculate diffusion coefficient. The input file required is the same. The output file name will be different, diffusion.xvg. Again, it will ask you to select one group. Any group you can select because all of them are argon only. If you do that, your value, see, can you see the value here? 12.1237. Within bracket is the error bar, error associated with the calculation, plus minus 0.3636 multiplied by 10 to the power minus 5 centimeter square per second. This is the diffusion coefficient of argon atom from your simulation. Diffusion coefficient is easily available for any solvent molecule, experimental data. So you can actually compare experimental data also. For water molecule, one more thing you can compare. You can actually check hydrogen bonded water molecules, how many hydrogen bonding water molecules are there from radial distribution function itself. So this is how you calculate diffusion coefficient. There are many other things you can calculate only from the XTC file. What is the density of solvent molecule around your ion pair or around any solvent molecule? Three-dimensional plot, how do you get? Everything you can calculate if you have the XTC file. Coordination number you can calculate from XTC file. So there are many other things that you can do with XTC file. For water also, the format is same. If you want to do simulation for water, it only depends on which water model are you using, whether you are using SPC, whether you are using SPC or TIP3P, TIP4P or ST2, whichever water model you are using, the format or the procedure will be same. You require a PDB file. Check the structure file of water. This is how it looks. So now you have 1, 2, 3. These are the coordinates of water. Each and every atom, oxygen, hydrogen. You can see here it is labeled as OW, HW1, HW2. SOL is the residue name. These are the coordinates. Connect means 1 and 3. So OW and HW2 are connected. 1 and 2, OW and HW1 are connected because these are bond lengths. 2, 1, 3, that is the bond angle of water. So this is how your PDB file form will look like if you go to slightly complicated system. Now again, once you have the PDB file, what you need to do, you need to go to INP file. You need to change the number over here. Now for water and for argon, density is different. So based on the density, you will calculate the number of molecules and based on the box length. So that will, so 30 angstrom box length corresponds to 899 water molecule. So once you have this, you have to execute your packmol file. How do you execute? /packmol less than water.inp. Once you do this, like this, something will come up on the screen. You will get your liquid water.pdb file. Once you have your liquid water.pdb file, you have to take it into another directory in your folder where you have created water folder. Then you have to convert it into GRO file because PDB is not the format used for GROMACS calculation. It is the GRO format used. It is GROMO structure file format used. Again, genbox is the command you will use. That is, it will box using your PDB file. Output will be in GRO format. This is minus box, cubical box of box length 3 nanometer. Once you do this, like this is something you will get. Reading solute configuration built with packmol. So your output file will contain these many atoms. Why 2697? Multiply 899 by 3, you will get 2697. Because each water molecule has 3 atoms. So 899 multiplied by 3 will give you 2697 atom. You can check the density 996.069 gram per liter, which is closer to the experimental density of 998 grams per cc. So what you have packed in your packmol is correct. Once you have that, you can view your GRO file. Your GRO file will have coordinates in nanometer. Each and every, see, 1 sol, 111 sol. That means this is number 1 solvent molecule. These are the coordinates. Then 222 is the second water molecule. 333 is the third water molecule. Like that, you will have for 899 water molecule. Then this is the force field or topology file for oxygen and for hydrogen. Since both the hydrogens are same, so even if you write only for one hydrogen, it will be taken care of. These are the mass, these are the charges, sigma and epsilon. Sigma and epsilon is always zero for hydrogen atom, no matter which system you take. It's always zero. Then again, the same format, what is the residue number and how many number of molecules you are taking. Once you have these, for energy minimization, what do you require? GRO file, TOF file, and .mdp file. So to perform energy minimization, you will do first grow MPP to create the TPR file. Once the TPR file is generated, you will do an MD run. Once you use this command -DEFFNM, it will produce all the output files in the extension with EM dot. So this is what you get. Steepest descent converged to Fmax less than 1000 in 22 steps. And it will give you the potential energy value also. So this is a global minimization that is done. Once your minimization is done, you will use the em.gro for full MD simulation. Same thing, full.mdp file instead of em.mdp file, full.tpr file output file name instead of em.tpr, and then followed by MD run. So it will give you set of output files with full as a initial. This is how it will give. This is the time required to complete. This is how you will get it. So how do you analyze the trajectory? First, you create an index file. Using the same command, make underscore ndx. Any GRO file, as I told you, you can use. So this is what it will show once you type out this command. So once you type out this command, you will see system water sol. Now here, in case of water, since you have different atoms involved, so you can actually calculate radial distribution function between two different sites or two different atoms. In order to do that, you can type out A. See, can you see here A? A means atom. So you type out A oxygen OW. So it will create an index with the numbers of oxygen of water molecules in it. So found 899 atoms with name OW because there are 899 water molecules. Then if you type out HW1, it will give again 899 atoms. Then if you type out HW2, it will again give you 899. At the end, you always have to type out Q because Q means save and quit. So once your index file is ready, you can actually do site-site radial distribution function between oxygen and oxygen. In order to do that, again, G_RDF, you will use the XTC file, TPR file for the full MDP, index file, and you can name the file name as oxygen water rdf.xvg. If you enter, now your index file will have these many groups. System water sol will always be there. OW and HW1 is what you have created now. Since you want to find out how water of oxygen interacts with oxygen of water, so you will select the same group 3 and 3 twice. Once you do that, you can plot it using XM Grace. This will look, the plot will look like this. So you have 1 peak, 2 peak, 3 peak, and after that, as I told, at larger distance, it reaches 1. Because GFR or radial distribution function is the ratio of local density to bulk density. After a certain distance, local and bulk becomes equal, so it becomes 1. This is between oxygen. Now between oxygen, hydrogen also, you can do the plotting, you can find out RDF, and what you have to type out is 3 and 4 instead of 3 and 3. Once you do, you get a plot like this, which is slightly different from the previous one. Now, oxygen-hydrogen graph will give you an idea about hydrogen bonding in water. If you get a peak like this with before 0.2 nanometer, before 0.2 means around 0.19 and all, that means there is a strong hydrogen bonding. And if that peak is quite sharp, you can see here the peak is quite sharp. So this peak means it has a very strong hydrogen bonding present in it. This peak is a result of that. So oxygen and hydrogen of water, this is how you get. Then the last one remaining is hydrogen, water, hydrogen, water. So instead of selecting 3 and 4, you will select 4 and 4 in the index file. Then you will plot the graph. And of course, please don't forget to change the file name as well. If you plot, you get a graph like this for hydrogen, water, and hydrogen, water. Then you can also calculate diffusion coefficient from the formula G_MSD. Input files are same, only output file name you will change. Now, in order to calculate diffusion coefficient, you have to select the whole system or water. You cannot have diffusion coefficient for oxygen atom or for hydrogen atom. If you do that, you see the simulation here was performed for 100 picosecond. So your diffusion coefficient is coming out to be 2.3789. Error bar is 0.0682 into 10 raised power minus 5 centimeters square per second. If you want to plot it, this is how the plot will look like. So these are the different type of calculations you can do using GROMACS software. You can do free energy calculations also. You can do, this is for the very simple system I have shown you. You can do it for protein in water also. You can start with S-peptide or lysozyme. Those are very small sized proteins you can start off with. And same way you can proceed for all those things as well. So, yeah. If you have any doubts as to what else you can do with the software, I'll be happy to answer the questions.
Right. Thank you very much, madam, for this marathon session. You have, thrown enough on them. They will be busy at least for 2 weeks or so. They can try all those commands. But yeah, are there any questions?
I can share all the files also. They can try it out.
Yeah, that will be great.
Yeah, I'll share it.
I have two questions. Hello.
Yeah.
One question is, here you have only single system that you have introduced, that is water or alcohol. Suppose we have a multiple system, or you can say binary mixtures. So for how can we introduce that to atoms or to molecules?
Binary system you are talking about, right?
Yes, ma'am.
Yeah, so for binary system also, you can, in the INP file, what you have, suppose you are doing for one more solvent, say argon only. So for binary system also, you have densities available. For basic binary systems, if you take water alcohol mixture, it's a very common mixture used for and one of the most studied mixture. So you get densities available at different composition. Suppose you want to do for 50-50 mixture. You have the density. Based on the density and based on what your box length should be, you can calculate the number of water molecules and number of methanol molecules you require, or alcohol, any other alcohol. Then in your INP file, what I have just shown. In this case, instead of ending your structure over here or ending your file here, you will repeat the same thing, structure water.pdb, number inside and end structure. You will repeat the same 4 lines again. Now, instead of water.pdb, you will write it as methanol.pdb or ethanol.pdb or propanol.pdb. So you will write one more line and you will change your number of molecules accordingly. So that will create your mixture PDB file. Once you have the mixture PDB file, it is easier for you to convert it into GRO file. Same command. Only changes you will get here is in your topology file. 2 files you will have your changes. One is the topology file, one is your PDB file. So topology file, what else you have to include? Apart from water system, you have to also include for your alcohol system. So include water.itp is written here. So Below that, you will just enter one more line, include methanol.it. Here, after OW and HW, you will put an enter and you will write for methanol. I am taking the simplest alcohol. In case of methanol, you have O, you have hydrogen, you have methyl group. So for 3 different atoms, you have to know, you should know what is the mass of each element, charge, and what is the sigma and epsilon. For hydrogen, as I've told, it is 0. Sigma and epsilon are 0. Then here, apart from Sol 899, you will have one more line with methanol, whatever residue name you want to give. For methanol, you will write here the number of solvent molecules you have taken. So only in topology file and in your initial input file that you are using for PackMol, those 2 places changes will happen. Apart from that, everything, your MDP file, no changes. So everything else will remain the same. If you want, I can share the binary mixture file with you all as well with the instructions, so you can do it on your own, and if any problem is there, you can get back to me.
Okay. And the second one is we have a RDF plot. Okay. So from that, shall we get that coordination number according to that?
Yes,
So
yes, you
basically, it
can
is
get. See, here,
So
when
how
you are
can we get
plotting
that?
RDF, here you are writing minus O, you are ending it here. If you type out another one command over here, space minus CN, and the file name remains the same with RDF, instead of RDF, if you write it as RCN, that is running coordination number. If you just change your file name and this output file format is minus O here, you write it as minus CN. Minus CN is coordination number. And then coordination number dot xvg. That will give you your coordination number, first shell coordination number you will get. Till here, it will integrate and give you the number. So if you open the file rcn.xvg, you can check at what distance your minimum is. It is around 0.3 here. So 0.3 corresponding to that in rcn.xvg, you will have one number. So that will correspond to the coordination number.
Okay. Thank you.
Right. Are there other questions?
Yes, sir.
Yes, please go ahead. Yeah.
Suppose I'm using some arbitrary molecule, then how will I create the topology file? Like, of course, I cannot create using PDB to GMX.
No, PDB to arbitrary molecule means for which there is no forceful parameter existing, right?
Yes.
Then for that molecule, you have to first optimize the structure using Gauss view or something. You have to perform a DFT calculation or Hartree-Fock calculation. From there, output file, you get the coordinates. Then you also get bond length there. You get the bond angles there. So from there, you take it and create your own topology file.
Okay.
In that case.
Okay.
Because all these files, all these parameters, they're actually taken from there only. You optimize a structure first using ab initio methods. Then in the output file of your ab initio file will give you details of bond length, bond angle, torsional angle, everything will be there. From there only the values are taken.
Okay. Thank you.